Hello, pre-calculus. Today you're going to learn about functions, some things that you already know, so it will just be a review, and other things that are new information for you about functions. First of all, you have the definition of a function, and the key is for each x that exists in the domain of the function, there is a unique y value. So if you have a 2 for x, you could have a 4 for y. But that means you can't have a 2 with a 3 for y. That would make it not a function. You could have the same y multiple times with different x's. That's not a problem at all, as long as each x has unique y. One of the things you can do is look at the vertical line test, and that just says if you can drop down a vertical line and it only hits the function once at any time, then it's a function. If it hits the curve more than once, then you don't have a function. These notes will also be provided out there on the Google Classroom for you. These notes about intercepts, increasing, decreasing, and constant parts of function and minimum maximums are available here, and these are mirrored in your book in Chapter 2, and you also did some work already in Khan Academy identifying these parts. So I would just read over these notes now. Another important note about a function is it smooth and continuous? So just this gives you an example of a smooth and continuous function here on the left. Continuous means that you can trace that function and you never lift your pen from the paper. And smooth means you don't have a corner or a cusp or a hole, so that, in this function over here on the right, it is not smooth, nor is it continuous. This is a function that we call piecewise, in that it has different outputs for different pieces of the domain. And we actually already looked at this example, but I wanted to do a little bit more with it. I could write this in functional notation as follows. F of x, the function of x, is such that it has 4 pieces. It will be x cubed when x is less than 0. The output will be 3 when x equals 0. The output will be 2 between the value of 0 and 4. And it is the square root of x when x is greater than or equal to 4. Note, there is no overlap in the x pieces, or you wouldn't have a function because you'd have different outputs for the same x. And that's how you write it in functional notation. On the next slide, we'll graph it. All right, so now we want to graph this piecewise function. You really just want to think about splitting up the domain in different pieces. So we're going to have a piece at 0. I'm just going to kind of draw a line down there so I can see it. A piece at 4. That's kind of another break. And that's about it. All right, so I'm going to start with the x cubed function whenever x is less than 0. So if I plug in 0 for x, 0 cubed is 0. So we know it does not include this point, but it's up to and not including that point. If I plug in a -1, -1 cubed is -1. And let's plug in a -2. -2 cubed is -8. So I know what the cubic function looks like, and it's just this part when it's less than 0. Next is the ordered pair 0, 3, so we'll just plot that. And that's why I do an open circle down below, because it cannot cross through both points or it would not be a function. Next we have at 2, from 0, not including 0 to 4. So right here 2, you're going to have an open circle at 0, and you're going to go across to 4 and another open circle. So the output is 2 for any of the values from 0 to 4, not including those numbers. Lastly, we have the square root of x when x is greater than or equal to 4. So I'm going to start with 4. The square root of 4 is 2. Oh, look, I fill in the circle because it happens to be that place for both those functions or pieces. Next, I'm not going to do the square root of 5, but I'll put in the square root of 9 because I know that one. It's a perfect square. It is 3. So 2, 4, 6, 8, 9 is a 3. And we know if we put in a 4, you'd be at 16. So we know what the square root function looks like. It's kind of something like this, going off in that direction. And that's what the piecewise graph looks like. Now that we have the graph, we can talk about the domain and range. Notice that you hit every value for x from negative infinity into infinity. So it's all real numbers for the domain. The range is a little bit harder. So I'm looking at the y values, and I can see I go from negative infinity, no problem, but it goes up to 0, not including 0. And then there's a gap, right, between, if I'm looking at the y values. It starts again here at 2. So if I'm looking at the y values, it includes 2 and will go up to positive infinity. So it's a union of both these outputs. We can also write that as follows. The range is y such that y is less than 0 or y is greater than or equal to 2. So there is a gap in the range. An important part of functions is also to be able to put or evaluate functions for different values in the domain. So if you have a piecewise function, you can do that as well. The key is you don't give multiple answers for the question. So let's look at these questions here. For the first one, it says find f of -3. So -3, when I look at my function, is only at this place. So -3 cubed is -27. And that's my only answer because it's only going to give an output at the appropriate place in the domain. Next one, find f of 1. That's right here. So the answer is 2. The next one is a little bit harder. It says find x if the output is -1. So you can look back at your graph, or you can kind of just figure out when you'll get a -1. And the only answer is right in here. And x would be -1. And when you do -1 cubed, you get -1. These last 3 questions have to do with transformations. What would the graph look like? So the first one's kind of easy. This is just a reflection over the x-axis. So what's happening here is all of these values just become negative. So you have -√x, -2, -3, and -x cubed. The next one, similar to the first one, you're just multiplying all the outputs by 2. So this is a vertical stretch times 2. So you would have 2x cubed, 2 times 3 is 6, 2 times 2 is 4, and 2 times the square root of x. The last one's a little more difficult because here what you're doing is changing the input. We know from our transformation rules that this will move the function left 1 value. And what you can do is just take each of these x's here and replace them with x plus 1. So when you take x plus 1 less than 0, it changes the function so that f of x plus 1 equals x cubed when x is less than -1. Running out of room here a little bit. Let's just erase this. So x is less than -1. It's 3 when x equals -1 because we're subtracting the 1. It's 2 when 0 is less than x plus 1 is less than 4, which leads to -1 less than x less than 3. And our last part, I'm going to run out of space here, is the square root of x when x is greater than or equal to 3. So it moved the whole function to the left 1. Another important skill when you're looking at functions is to be able to find the domain of the function algebraically, or being able to do it without looking at the graph. So here's 2 examples, and the key is you have 2 real things to look for. One, you cannot divide by 0, so that would give you holes or gaps in your domain. And likewise, you cannot take the square root of a negative number. So in rational functions, when you have the variable in the denominator, you're going to have problems in the domain. And also in square root functions, you've got to make sure that entire quantity under the square root symbol is greater than or equal to 0. So those are the main reasons why the domain of a function would not be all real numbers. So let's answer these questions. With the first one, what I want to do is factor the denominator as much as I can. So this we know is a difference of squares. It's x plus 2, x minus 2. So that means that denominator becomes 0 if x plus 2 equals 0 or x minus 2 equals 0, which means x equals -2 or x equals 2 are our problems in the domain. So we know that the domain for this one is all real numbers except x may not equal 2 or -2. Sometimes we write it like this as well. The real numbers except x such that x does not equal plus or minus 2. Okay. In the next one, it's the second reason, cannot take the square root of a negative number. So that means I take what's under the square root and I make sure that it is greater than or equal to 0. So I just have to solve this inequality. So I have -3x greater than or equal to -4. I'm dividing both sides by -3, and you end up with x. And it's going to switch the sign when you divide by a negative. So x is less than or equal to 4/3. Remember, negative divided by a negative is a positive, and that is the requirement on the domain. So the way we write that is then the domain is all real numbers, x such that x is less than or equal to 4/3. So, and you should just test that real quick. So pick a number that's less than or equal to 4/3. 1. Right? That means 1 should be valid. If I plug in a 1, I end up with the square root of 4 minus 3, which is the square root of 1, which is 1. Works perfectly well. But if I plug in a 2, which is greater than 4/3, 4 minus 3 times 2, which is 6, you end up with the square root of a -2. We can't do that, right? That brings us into imaginary numbers. So those are the two ways algebraically to identify the domain of a function. All right, we're moving right along. The next is a feature or characteristic of functions called even or odd. And even and odd functions is something that I want you to be aware of, especially for when we get into trigonometry. So let's just look at the definition first. An even function is such that if you take f of -x, you're going to get the exact same function. Now, if you look at a graph of that, you'll see symmetry with respect to the y-axis. So let me give you an example. If I look at this function here, f of x equals x squared, this one's going to be an even function. So f of -x is -x squared, right, in parentheses, which means x squared. I got back to the same function, so it's even. And if I look at the graph, that's a quadratic, a basic quadratic function. Do you see the reflection over the y-axis? So you can look at a graph and know if it's even as well. An odd function, on the other hand, is when you plug in the opposite of x into the input, and it actually changes the sign of all the outputs. So let's look at an example there. How about this one? F of x equals x cubed. All right, so that means f of -x equals -x cubed, and you've got -x times -x times -x, and you end up with -x cubed. Note that my original function has now changed to be its opposite. So a cubic function is an example of an odd function. And let's look at the graph because there's symmetry here too. So here's what your cubic function looks like. And note, this is something we call point symmetry around the origin, so that if I rotate it 180 degrees, I end up with the exact same function. So that means it's symmetric with respect to the origin. And there's a number of different graphs that have that. Now, not every function is even or odd, so your third option is neither. And to tell you the truth, most functions, and especially ones with transformations, will be neither even nor odd. But when you know a function is even or odd, and you're going to see the trigonometric functions we study later, it's a very helpful trait to know about the function. So let's answer the next 4 questions. Are the following functions even, odd, or neither? So what I'm going to do is just algebraically plug in negative x and see what happens. So this first one, negative x quantity squared minus 5, and I end up with positive x squared minus 5. No change, so that is an even function. You can also think about it graphically. That's the quadratic, move down 5 on the y-axis. Let's look at the next one. G of negative x is negative x cubed minus 1, which is negative x cubed minus 1. Now you may say, oh, that one is odd. Well, it's not, because both terms need to change sign, right? So let's just look at what negative g of x would have looked like. That would be negative x cubed minus 1 or plus 1. So it would mean you have to distribute that minus. So these are not equal. So this one is not odd, it is neither. All right, why don't you pause the video here and try 3 and 4 on your own. All right, here's 3 and 4 completed for you. So when you plug in negative x for h, you end up with this quantity, which is the exact opposite of the original quantity. So this is an odd function. And the last one is the absolute value function. When you plug in negative x, you end up with the same value, and that is even. And just to remind you, a graph of the absolute value function looks like that, which has beautiful y-axis symmetry. All right, these last 2 slides are going to be new for all of you, and they're very much related. The first one is to find the average rate of change of a function. So here you have a function curved in blue, and the average rate of change, what you want to do is find this between 2 points. So I chose point A and point B. And really what it is, if you connect those 2 points, it's the slope of the secant line that crosses through the function at those 2 points. So we're really just calculating the slope of this line here that connects those 2 points in that curve. So here is the formula. And note, I hope you see that it looks very much like slope. Remember, f of b is the output of the input b, and f of a is the output of the input a. So if you think about slope being y2 minus y1 over x2 minus x1, we're just finding the slope of that line between those 2 points. Let's go ahead and look at the example down below. First of all, you have to be given the function that you're finding the average rate of change for, and then you have to be given the 2 points. So if I want to do the average rate of change for f of x equals 3x squared from 1 to 3, I need to find f of 3 minus f of 1 divided by 3 minus 1. So the output of the 3 minus the output of the 1 divided by 3 minus 1, my inputs. So let's go ahead and do that. So 3 times 3 squared minus 3 times 1 squared. I'm just using the function and plugging in the x value over 2, which is 3 times 9 or 27, minus 3 times 1, which is 3, divided by 2, and I end up with 24 divided by 2, and I get an average rate of change of 12. Now, this function isn't graphed, but what you want to see is from 1 to 3, it's pretty steep between those 2 points, 1 and 3 on that function. So let's just look at that real quick. 3x squared is a very vertically stretched quadratic. So if you look at from 1 to 3, look how steep that line is. And so a slope of 12 makes sense. All right, why don't you pause the video and try to do the same thing for 2 and 3 using that same function. All right, take a look here. So the answer to number 2 was 18, and I show you the work over here. And you can see you end up with 75 minus 3 over 4, which is 18. With number 3, it got to be so large that I actually kind of showed you a trick here. When you do f of 7, we know it's 3 times 7 squared minus f of 4, which is 3 times 4 squared, all divided by 7 minus 4, which is 3. Those 3's cancel, so it's just 49 minus 16, and the answer is 33. And you can see, we saw what this graph looked like. It's getting even steeper as you get further from 0. Okay, this is your last slide about functions. This is something called the difference quotient. In this one, you're trying to find this special calculation for any number x in the domain of a function when you're given the function. And it really is just going to give you a new formula. And I hope you see how this is related to the average rate of change, because what you have is that difference, which was the h value, and that was the difference of the two inputs, and then you have the function with the value added minus the original function. So, and just kind of in words, the difference quotient of a function equals the average rate of change for a point x and a point h away from x on its graph. So you can pick your starting point, and you can pick how far away you want your x to move, and then you can calculate this formula to find what that average rate of change is. So let's do the first example. So I'm using my function of x squared plus 1. So I'm going to first write down f of x plus h, which is x plus h quantity squared. So everywhere there's an x, I replace it with x plus h, plus 1 minus the original function, which in this case is x squared plus 1. Don't forget, you're going to have to distribute that minus. You're subtracting the whole function x plus 1, all divided by the variable h. So we have to FOIL that out. You get x squared plus 2xh plus h squared plus 1 minus x squared minus 1. And if you're doing this right, a whole bunch of things should cancel. So this cancels with that, because x squared minus x squared, this cancels with that. And this, of course, was all over h. Now we have 2xh plus h squared over h. Once again, you're going to see things disappear. These h's can all cancel. And our final answer for the difference quotient for the function x squared plus 1 is 2x plus h. So if you're given your starting value and you're given your change in x, you can find quickly that value for the average rate of change, or the slope between those 2 points. All right, I'm going to pause the video, and I would like you to try the last one on your own. Understand this last one gets a little bit harder. There's a lot more going into it, but give it a try. All right, here you go. So there's a lot more work here. Remember, everywhere there's an x, you're replacing it with x plus h in the first part. Make sure if there's a minus that you'll be distributing it on that whole quantity. And then, of course, you subtract your original function. I FOILed out the x plus h squared. I distributed the minus on the original function over here. Then I distributed the 2. And then I looked for things that cancel, and of course 2x squared and 2x squared, and x and 1 and 1. And you end up with this here in red. And then the h's, as long as each term had an h, I can cancel those h's with that division of h. And I'm left with 4x plus 2h minus 1. Don't forget the minus 1. When you cross up that h, you're left with h divided by h, which is 1. So there you have your difference quotient for this function here. That concludes the additional work in functions that I wanted you to learn.